Previously, we studied dynamics in linear systems. So now we're going to take a look at dynamics in rotational systems. So we're going to start out by assuming we've got a mass here going around in a circular path, and it's a distance r here from the center. And if we apply a force on that mass, it'll be accelerated according to Newton's second law, F equals ma. But now, if we substitute in our relationship between linear acceleration and angular acceleration, we get F is equal to m times alpha times r. And now we're also interested in torques in rotational systems, so if we multiply both sides by r, we get F times r equals mr squared times alpha. And of course, torque is equal to Fr, so now we have torque is equal to mr squared times alpha. Now, we can apply this same treatment to systems composed of many particles, but we would need to compute this mr squared term for every particle in the system and then sum them up. So when you do this, this is what's known as the moment of inertia of the object, and the moment of inertia, I, is defined as the sum of all of the mr squareds for all the particles in the system. So then this gives us the rotational equivalent of Newton's second law, which is torque is equal to I times alpha. Notice that I here, this moment of inertia, is sort of analogous to mass in linear systems. So here's a little problem that will illustrate some things about this moment of inertia. We want to compute the moment of inertia for 1 kilogram particle on the left and a 2 kilogram particle on the right. It's on a massless rod, 1 meter long. Two situations. One, when the point of rotation is in the center, and the other, when the point of rotation is 0.25 meters to the left of the 1 kilogram particle. So you can see a little diagram down here. Here are the two particles, here and here, that's 2 kilograms, 1 kilogram, and we'll start out first computing the moment of inertia when the point of rotation is right here in the center. Okay, so I is equal to the sum of the mr squared. So we'll have to do an mr squared for this and an mr squared for this, sum them together. Okay, so for this one, we have I is equal to 1 kilogram times 0.5 meters squared. For this one, we have 2 kilograms times 0.5 meters squared. We calculate the individual values of I. So for this one, it's 0.25 kilograms square meters. Notice those units. And this one, 0.5 kilograms square meters. We add those two together, we get 0.75 kilograms square meters. Okay, now let's take a look at the second one. When the point of rotation is out here, 0.25 meters to the left of the 1 kilogram particle. Okay, we do it the same way. We want to compute the sum of the mr squareds. So for the first one, I is equal to 1 kilogram times 0.25 meters squared. And then the other one is 2 kilograms. And now we've got this long distance of 1.25 meters squared. That's the value of r. Okay, so we compute the value of the moment of inertia for the 1 kilogram particle. It's 0.063 kilograms square meters, and the other one is 3.13 kilograms square meters. Okay, we end up with a moment of inertia here of 3.19 kilograms square meters. Okay, so a couple of things to note here. First of all, look at the big difference between the calculated moment of inertia here and here, and the difference was because the point of rotation was moved from the center here to here. And for this case, where the point of rotation was out here, notice how little this mass contributed to the total, only 0.063 kilograms square meters, and that's because it was so close to the point of rotation. This one out here, this mass, contributed almost the entire thing, 3.13 kilograms square meters. So, for moment of inertia, it's very important not only what the mass is, but how the mass is distributed. The mass that is farthest away from the moment of from the point of rotation is going to contribute most to the total moment of inertia. This mass close to the point of rotation contributes hardly anything. So now what happens if you have larger objects that you need to know the moment of inertia for? Well, there are certain mathematical techniques that have been used to get formulas for common shaped objects. And those, we're just going to use the formulas for these objects. So the first one is a hoop. And for this one, I is just equal to mr squared. If it's a thin hoop, then all the particles have pretty much the same distance from the point of rotation. So this one is just mr squared. The next one is a solid cylinder or a disk. The axis of rotation is shown here. That one is I is equal to mr squared over 2, 1/2 mr squared. Then we've got a rod here where the axis is going this way. That's 1/12 mr squared. Here we have a solid sphere. The solid sphere is 2/5 mr squared. And then finally the hoop, again, same here as here, but this time the axis of rotation is shown vertically here. And so for that shape, it's, again, 1/2 mr squared. Here's an example of a problem that deals with the rotational equivalent of Newton's second law. We've got a father pushing with a force of 2.5 times 10 to the 2 newtons on the edge of a 50-kilogram merry-go-round, which has got a 1.5 meter radius. We want to compute the angular acceleration first when no one is on the merry-go-round, and then when an 18-kilogram child sits 1.25 meters away from the center. We're going to consider the merry-go-round to be a uniform disk. So we're going to start with the rotational equivalent of Newton's second law. Torque is equal to moment of inertia times angular acceleration. And we're going to solve for alpha, the angular acceleration. So that's the torque divided by the moment of inertia. So the torque is the force times the distance from the point of rotation. So the force is 2.5 times 10 to the 2 newtons, and the merry-go-round has got a radius of 1.5 meters, so that's 375 meter newtons. Now, we need to compute I. We're going to assume that merry-go-round is a uniform disk, so if we consult the chart on the previous slide, we can see that the moment of inertia for a uniform disk is 1/2 mr squared. So it's 1/2 times the mass of the merry-go-round, that's 50 kilograms, and its radius is 1.5 meters. We square that, so that's 56.3 kilograms square meters. Now we can solve for the angular acceleration, 375 meter newtons, the torque, 56.3 kilograms square meters, the moment of inertia, so that's 6.66 radians per second squared. Okay, now for the second part, where the child is sitting at this distance away from the center, we need to compute the moment of inertia of the child sitting there. So we are assuming that the child is sort of a single point on the merry-go-round. So we're going to compute his value of I as being mr squared. So we've got the mass of the child times his distance from the center, 1.25 meters. So that gives us 28.1 kilograms square meters. Now, to get the total moment of inertia of the merry-go-round with the child sitting on it, we have to add that to this value over here, Okay, so that gives us 84.4 kilograms square meters. This is the now total moment of inertia of the merry-go-round with the child on it. So now the angular acceleration is equal to the same torque. That hasn't changed, but this new moment of inertia. So now the angular acceleration is 4.44 radians per second squared. Notice that the angular acceleration has decreased as the moment of inertia increases, much like in Newton's second law, when you apply the same force, but the mass gets bigger, then the acceleration gets smaller. So this is exactly analogous to that.